We're going to start with this panel discussion on power electronics and its impact on coil-winding industry, motors, generators, and transformers, essentially. We have a number of very good panelists here today, and I'm going to let them introduce themselves in 2 minutes. I just want to introduce the reason why we think this panel is important. So power electronics has had a tremendous influence in motors, generators, and transformers over the last years. And this panel discussion is intended to clarify and to precisely define what are those impacts, what are the threats and opportunities that will be available here for those that produce coil-winded system machines, mostly in power transmission and distribution, mostly for the power grid. So that is the area: motors, electric motors, generators, transformers for energy transmission and distribution. That is the area where power electronics are going to have a huge impact, and is having already. Not so much in maybe in low voltage applications. So this being said, I really hope that this discussion will clarify these issues. We're going to start with a brief introduction of every panelist, and they will explain the keynotes of their points of view. Then we will have a few questions asked, and then we will open the floor for Q&A from all of you. And, well, I'm going to act at the same time as a panelist and as a moderator, because we kind of failed with the moderator that we had in mind at the last minute. So sorry to be taking both sides. But this being said, I'll leave the ground to all the panel members. So perhaps starting from the end, if you want. Sure. Please.
Thank you, Daniel. My name is James Tabby. I'm here actually in 2 roles. As the president of RAF Tabtronics, our company designs and manufactures ultra-high power density transformers, coils, and inductors, mostly for defense, aerospace, and other high reliability, highly engineered markets. So I actually come from more from the low voltage side than the power distribution side in my day job. But I'm also here representing as the president of the Transformer Association, which is a North American association of transformer manufacturers and suppliers to the industry that really serve the entire gamut of transformers. And I guess my position in terms of the question on the table is that the changes that we're seeing in power electronics and power systems and power distribution are only good for the transformer and coil winding industry. It may force a shift from the traditional large, high power distribution type of transformer manufacturer to higher efficiency, higher voltages, higher frequencies. But there are a lot of people that are already playing in that space that will be able to serve those markets.
Thank you. James, Alex?
Hey, good morning. My name is Alex Huang. I'm a professor at the NC State University. And my specialty are power electronics and power semiconductor technology. So I have been working in this field for more than 20 years. So back in about 2007, 2008, we have established the FREEDM System Center with some government funding and industry university partnership with many industries. Some of them are here in this exhibit, to look at key technology needed to transform the electric power grid into a more actively managed and controlled grid. So one of the key technology that we foresee that's needed for the traditional grid is to have a much better small transformer at the end of the distribution grid, at the edge of the grid, that can deliver the value to the utility industry, and so as a key technology. What really made this a possibility at that time was really looking at, number one, the semiconductor revolution that's happening in the industry that now can go to the voltage into tens of and 20s of thousands of volt range, really able to impact the utility voltage class in the distribution side. So that has not happened in the last 50 years until very, very recently. That was really a key moment. So we have been working on this technology for the last 5 or 6 years. It has made numerous academic and research progress. And one of our work was cited by MIT in 2011 as one of the 10 technologies that could change our country and our lives. So coming back to this topic today, my position is the industry is changing anyway, no matter what. But for the particular utility industry and the transformer manufacturing industry, I think this is a great opportunity, not a threat, because we all have to adapt to the new market and new energy infrastructure needed. For the utility company, this technology is really positioned at solving the headache problem they have in voltage control, in integrating renewable energy, electric vehicle, and photovoltaic. All these new things are happening at the consumer side. They have to do something, and this is one of the key technology we believe will provide the opportunity for the utility industry. For the power transformer industry or semiconductor industry, so these are two industries that potentially will greatly benefit from this opportunity too. This will create new jobs and new market. And for semiconductor, this is true, we will need new medium voltage semiconductor technology. So our friends sitting on that side represent one company in that space. And for the transformer company, we still need transformer. We still need inductor. We need another magnetics, but they all have to be designed for different requirements. We need higher voltage and higher frequency and higher efficiency in a very compact space. So it's much, much harder to do. So that's one research we are working on. So I think it's a great opportunity. It's just a different challenge. So we hope that we can engage the dialogue. I hand over.
Thank you, Mike.
Yeah.
Rick, do you want to come to the slides?
Sure, yeah. Morning, I'm Rick Hoadley with ABB. I'm a Principal Consulting Application Engineer with them. And I've been in adjustable speed drives for playing around with them for about 40 years with DC drives and AC drives as adjustable speed and adjustable frequency. And it's been interesting to see really what happens when you use a drive in any type of an application. And this also applies to UPS type of systems. It applies to any type of power conversion that's taking place, even with your power supplies you have for your laptops, and with low energy type of light bulbs. And just a quick picture here. The things that occur when you have a drive in the system, on the input line side, you've got all these current pulses coming in, and the current does not look like a sine wave any longer. So you have to deal with that. So the transformer or the generator that's supplying that power has to be able to handle those current pulses. Again, because you've got these harmonics associated with it, which can cause extra heating and it cause voltage distortions, which could be a problem for other pieces of equipment attached to that same supply source. On the motor side, you've got voltage pulses. Again, it's no longer a sine wave, and these voltage pulses do a number of different things to you. But first, on the line side, there's a lot of different solutions for doing that. And I'll be giving a talk later on today just talking about the line side harmonics and how they can be improved. But on the motor side, this is really where the difficulty arises. Because if you take a look at it, what does the output look like from a drive or from a UPS type of system? We've got large peak voltages from phase to ground. Well, what does that do? That's an increased stress on the insulation system for that motor. Or if you have a filter on the output, that reactor that you have out there has to handle that same thing. And what does that mean? That means reduced motor lifetime. What about the peak voltage phase to phase? Again, those are high voltages, higher than the normal peak voltage you see with the AC line voltage. And again, that's an increased stress on the insulation. Again, reduced motor lifetime. The rate of rise of that voltage is not like at all what it is with a sine wave. The sine wave, we're talking about 1 volt per microsecond or less. With drives and fast switching devices, we're talking about like 3,000 volts per microsecond. That has an effect things become looking like capacitors now simply because of that high DVDT. And not only that, again, there's stress on the insulation. Things show up as first turn failures, and these are again issues you have to deal with. And what does that mean? That means reduced motor lifetime. What about the neutral point in the motor? That's going to be jumping around because we don't have three-phase sine waves going to that motor. And again, that means you can see partial discharge in the bearings, bearing currents, so bearings fail, and again, that means reduced motor lifetime. And besides all of that, the current waveform, well, the current waveform looks fairly nice. There's a PWM waveform. There's a little bit of harmonics in there, but it does mean there's going to be a little bit of additional temperature rise in the motor. And again, what does that mean? Reduced motor lifetime. So how do we really deal with that? How can we really get our motors and our drives working together and be more of a uniform way of cooperating with one another? A lot of times problems occur in the field, and the motor manufacturer says, well, it's that drive. And the drive manufacturer says, well, that's a cheap motor. You know, why don't you get something better than that? And so this is where I think we have to work together much more closely to be able to improve that motor lifetime as a result of these things. Sure.
It's a high bar. Thanks, Rick. I didn't bring any slides.
Oh, okay. You want to use mine?
Wait. My name is Chad Eckhardt. I'm president and CEO of GridBridge. GridBridge was formed in January of 2012 as a commercialization arm, or a company taking technology out of the base research of different organizations, namely FREEDM System Center, and bringing it to market. So we're harnessing power electronics in a way that they haven't necessarily been used before. We're combining them with embedded software. We're really introducing some breakthrough power delivery systems inside a variety of applications. Now, specifically in the utility market, we're introducing our Grid Energy Router platform. It has multiple products that do sit at the transformer level, so downstream of downstream of the substation, and really have the capability in the future to introduce high voltage to low voltage conversion function. I can say that we are very proud of the progress we've made thus far in working with utilities. We have made it to pilot programs, and we are live at some of the nation's largest utilities with this particular technology. So for the naysayers who say it isn't coming, we tend to view differently because we're live on utilities. The progress, again, is there. The main point that I'd like to have everybody take home with them is that as we look at power delivery systems, there's always some ability to connect or sense or control. But realistically, what we're seeing the need is to be able to combine all of those. And to combine all of those is a very powerful solution: connect, sense, and control. So we're doing that today downstream of the substation. We're doing that because of the introduction of renewables and the need for the power delivery systems. Again, these can be many different power delivery systems to be much more efficient and to be able to route power in a way that it historically hasn't been done.
My name is Jeff Casady. I'm with CREE Incorporated. What CREE does is focus on silicon carbide for power systems. We've also got a lighting brand that you probably have heard more of, but it's similar in the sense that we're taking semiconductors and we're applying them in markets that either it's revolutionizing it or it's just changing it completely, where semiconductors weren't there before. So lighting is a great example because the light bulbs were either your incandescents, and then those got phased out eventually, and then you had more of the compact fluorescent lights, but now it's going to solid state. Your LED, that's all semiconductor solid state. So downstream you can think of even integrating more electronics with your light bulb now because you have a solid state semiconductor based light bulb. And we're trying to do the same thing in power. Where we've started silicon carbide power is the diodes have been out for about 12 years, but we started in the 650 to 1700 volt range. It's very typical, so it's not interfacing with utility type applications at first. But they are very reliable, they're very high efficient. You see them in a lot of the hybrid electric vehicles. Silicon carbide's being used already in these vehicles now. And we've come out with more lately the power switch, which power MOSFETs, power modules. And between CREE and other suppliers, we've gone from maybe 4 years ago, no switches, no modules in the market with silicon carbide, to now there's literally dozens and dozens of these products available. And they're going into the renewable markets, the solar inverters, industrial power supplies, induction heating, and so on. But where we see the future is this base technology scales up in voltage very, very, very easily. Unlike silicon and silicon carbide, you can go up in voltage without any problem at all. In fact, it wants to run at the higher voltages. So we can make 10 kV, 15 kV, and even 25 or 30 kV solid state switches. I think in the near term, we think up to 15 kV is very feasible for the MOSFETs. We know that customers have made solid state transformers using these MOSFETs, and it doesn't eliminate the transformer, but it does in the conventional sense. It's more of a higher frequency transformer that Alex referred to. But this starts to enable complete new functionality. As you see the grid move towards distributed power for renewable energies, you can have more kind of intelligent control of the power when it comes on and off, and have these solid state transformers. So from our standpoint, we see the components, the technology in silicon carbide at least, very mature and rapidly maturing for this application. And we're interested in learning, I think, where it goes from here. So that's why I'm glad to be on this panel.
Thank you. Turn as a panelist. So I am with a Spanish company called INAEL Electrical Systems that manufactures equipment for the medium voltage power transmission and distribution grid. But more than that, I'm here representing as a coordinator of Project SPEED. This is a European Union project funded with $20 million. We're 17 entities between companies and research institutions from 9 countries in Europe, and we are essentially working on silicon carbide for energy transmission and distribution. So with the end view of putting solid state transformers and real devices, high voltage devices in the power grid. So essentially this tells you that this is European Union money, country people's money somehow, that was awarded to a specific project in a very large competition. And it tells you that the governments and the decision makers, they do really see this as a future. They do really see this as something that it's going to bring a complete revolution to the way we understand energy transmission and distribution, power distribution. It's going to increase efficiency. It's going to provide much more performance than the older system, and it's going to create opportunities for every one of us. So that's essentially the key idea, and that's the reason why I'm here as a panelist. And well, so with that, I think that I am back to moderator, and we've been introduced ourselves, and I think the idea now is that I will ask a few questions to all the gentlemen in this panel, just in order for you to know a little bit more about this, and then immediately we will open for Q&A to everyone. Although, let's be clear, if any one of you have any question at any moment, feel free to interrupt and ask. It's much more important to answer your questions than to do any other thing. So at any moment, just ask, okay? So this being said, I think there are a few things that could be clarified, that could be made a little bit better. Let me just review my notes. So for example, I think that everyone here in the audience would like to know how a conventional manufacturer of motor, anyone in the coil-winding industry that has been producing motors over the last decades or something like that, what could they do in order to really benefit from the advantages that variable frequency drives and power electronics provide? So it's just a passive attitude, like you said, I bring the motor, you bring the drive, and that's all, or they can do something active to benefit from that?
Well, certainly there is an active sense to this because of problems that have been seen in the field. Now, there wasn't much seen in terms of problems before about 1990. Devices were slower, and you didn't see reflected wave issues at the motor terminals. A reflected wave is where the voltage steps up to about 2 times what the DC bus voltage is in the drive. So if you have like a 480 volt motor, it might be seeing voltages about 1300 volts at the terminals, and that was causing motors to fail. So we started wondering, okay, what's happening here? What can we do about it? What people started doing was putting filters on the output of the drive and talking to the drive manufacturers. We found some motors would fail within about 2 or 3 weeks. Other motors would fail maybe after a couple of years. Others wouldn't fail after even 5 years. And I started, wondering, well, what's the difference between these motors? Certainly the ones that failed within 2 weeks were very cheap. And started wondering, well, what made them cheap? Why did they fail? And it's really because they didn't have phase paper in there, they didn't have slot paper in there, and so it was a lot less expensive to produce, but it also meant they would fail much more rapidly. There was partial discharge issues with those types of motors and the installation system. So really working with the motor manufacturers, it's saying, all right, we need to have really a tougher insulation system than what has been used before. Maybe like a double coating on the insulation, not just a single coat. Some are for medium voltage drives and motors, they might have a couple of wraps of insulation on there, not just a single wrap. Again, to be able to handle these higher voltages that they're seeing and to reduce the possibility of partial discharge in these motors. So both these groups have to work together on this to come up with say an economical solution. We can't push it all off into the motor, and you can't push it all off into the drive. I think we have to work together on that.
Great, thank you. Thank you, Rick. So another question, I have a similar question for Jeff from CREE. Similar question in the sense that, do you think that there is a way in which coil-winding manufacturers, people that produce motors, generators, transformers, can directly benefit from the devices, from the new generation of devices, like gallium nitride, silicon carbide, that you produce, or you see you as a device manufacturer more as a hidden supplier that is going to supply to all the layers, and then that's going to be integrated in the final solid-state solution? That's my question.
Sure. Well, certainly we don't plan on making the solid-state transformer, so that would be more like Chad or someone else would be making that. But I think for the application side of it, it should open up new applications for the manufacturers. I think Alex touched on some of this as well, but as the way power is distributed in the grid is changing, there's going to be opportunities for solid-state transformers to come in where a conventional transformer just simply wouldn't work. It wouldn't fit physically, or it wouldn't have the functionality that people are looking for it to have. So I think it's going to open up new opportunities and new markets.
This is a little bit more for both Chad and Alex, in the sense that it's related with the solid-state transformer. So first thing that I have in mind is, of course, I think this is the most clear case of a potential technology that would perhaps completely substitute the technology that is today in the market, perhaps. So I think the main concern or question that comes to mind is, what agenda do you envision for this? So do you think that there's a technology that's gonna really sweep the conventional manufacturers from the market, or quickly, slowly, it's gonna have the niche market and everyone is gonna be able to coexist? What do you think about, first Chad and then Alex, what do you think about the substitution of conventional transformers with solid-state transformer technology?
Yeah, so thanks, Daniel. I think that, any market takes a significant amount of time to transition in technology. We can cite numerous markets out there, and to say that it's going to be a broad sweeping change is completely false. I think we're going to see an evolution, and we're already seeing that evolution today, transitioning, and I'll pick on the utility market, right? Realize that that transformers and these solid-state transformers can be used in many different applications: traction, aerospace applications, military applications. But if we just pick on the utility market for a minute here, and we look at the size of that market, and we look at the fact that 63 million transformers, according to DOE, are installed in the U.S. alone. These are distribution transformers, not substation transformers. Estimated 500 million distribution transformers worldwide. That's a pretty significant market size to address. And so what we're seeing is that even, again, a fraction of that is a notable adoption piece. Now, in working with utilities over the last 5 years, we don't expect them to rip out every of the 63 million transformers in the U.S. and start fresh. That's not going to happen. What we're seeing instead is an evolution of technology, and the evolution is taking place now. Offering the benefits on the secondary side of the transformer with some revolutionary and to the market MOSFETs, IGBTs, and offering the utilities the benefits that they want to see today, but doing it on the secondary side of the transformer is offering them the comfort with managing and dealing with power electronics on their grid, because this is something new. Now, to introduce the high voltage to low voltage conversion function, you just heard Jeff and you'll hear Alex talk a little bit about the readiness of technology. So that train has left the station and is moving forward. We're ready to receive it. We're working on the marketing piece and the readiness of the utilities to accept that technology. And again, it happens in an evolutionary path. We can talk about time frames and more specific on products if you want, but I'll give Alex a chance to chime in first.
Yeah, I definitely agree with Chad that the new technology need to take time to get into the market. So Chad's company is already introducing the technology at an acceptable price and at an acceptable entry level to deliver the benefit we envision in the solid state transformer or the smart transformer technology. But long term, the message I want to give to everyone who is in the either utility side or the traditional transformer manufacturing side, this technology should not be looked at as a replacement technology for the 60 Hertz transformer function. This is completely new technology to empower a new energy infrastructure. So we have to look at the benefit side much more in order to justify initial higher cost. For the long-term solution, we want to use the high voltage power electronics technology to replace to do the solid state power conversion. The key in the technology is how do you do power conversion at high frequency at a medium voltage level. That will enable a lot of application as a key enabler. I can give you an example we did in a cost-benefit sense. If you just look at replacing a 60 Hertz transformer, the only function is just step down the voltage. You will never be able to justify the cost for a long time. But if you look at today, the need to charge an electric vehicle as a key application, very soon you can find immediately justify this technology even in today's dollar. Today, if you want to charge an electric vehicle, you have to install a transformer, 60 Hertz transformer, followed by AC to DC conversion unit and a DC-DC conversion unit at 50 kilowatt or higher. That will cost you more than $30,000 to do it. With this technology, you can do this in one step, and at a cost maybe at half of the cost, and at efficiency point even higher. Okay, so that's just one example. Another example is the PV industry. Today, in order to integrate a PV farm to the utility grid, and it can be into a high power inverter that does DC and DC to AC that converts all the DC that to replace that with the solid state transformer with the intention to directly connect the PV inverter. In this case, we only need one DC-DC state. It will immediately see not only cost reduction, but also DC-DC gain. So these are the message we want to give to the utility industry or to the manufacturer, that you have to, depends on how you look at it. So overall, it's going to be a long term to penetrate the dominant market of the voltage conversion market, but the emerging market is really important. And utility have a voltage issue, have a demand side management issue, has a customer low voltage problem, can immediately justify a lot of this benefit. And the loss reduction on the feeder is also substantial. So, and we have published some of those papers. We're going to continuously to do so to get the benefit out there because you always get a question for industry with such a long history, reliability and cost, we simply only talk about these two numbers, but it is not the right way to look at the problem. That's my opinion.
I agree with Alex, and we just spin around, and if I can just add a little bit more to that. Again, I mean, I fully agree. I mean, we're looking at the totality of the electrical distribution network and the benefits that we're offering. When you look at the integration of renewables, when you look at the driving utilities to better route power, and I mean, you can justify many of these technologies by looking at one large outage across a region, and being able to better route outage to some critical loads is very valuable. But add on that efficiency and the drive for efficiency. Again, these components start to look much more attractive, or these devices. So again, I agree fully. We look at the totality of the electrical distribution network. We work with utilities and have worked with these utilities, and I think we started back in 2009, 2010, and we started off with a list of somewhere around 14 or 15 benefits that we can offer. And again, high voltage to low voltage conversion function is there, but it's not the core focus. It's tying in renewables. It's all these other things. It's mitigation of harmonics. It's routing of power. It's things of that nature. It's direct DC connectivity, elimination of inverters, whatnot. So.
Thank you. Yeah. Well, I would just like to add that probably summarizing what it is clear is that this technology is not going to be widely implemented in a year and substitute. I mean, conventional coil-winded transformer manufacturers and solid-state transformer manufacturers potentially, they will live together for a long, long time. And there will be niche markets where all this performance, this extra performance that a SST, a solid-state transformer, will add will be more than welcome. And there will be many other markets where people just don't need it, and you will not be able to convince anyone to make any use of this extra performance. So I think there is a common opportunity here to grow the market. And there is also one thing that never forget that in the core of a solid-state transformer, there will always be a high-frequency conventional transformer. So it will actually create opportunities for those producers that are able to produce very high quality, high frequency coils and transformers that will be actually needed to produce ultimately any solid state transformer. So okay, so with this being
That's
said,
a good point. We're winding our own today, and so there's a huge opportunity again to work with folks. And so high frequency transformers. I mean, it's a pain point.
I think that's going to be a large opportunity, right?
We can help you with that, Chad.
Perfect.
Perfect. Manufacturer here.
I was hoping.
I had a question for you, finally, James. Although this thing of the high frequency transformer is a good point, but okay, in your role representing the Transformer Association, so you're representing a number of manufacturers that are members of your association. So my point is, have you given a thought to this thing? Do you have any common position about what is if there is any danger, or we just see what happened? Do you have any position about this issue?
I have my own opinion. I would say the Transformer Association doesn't have a statement at this point, but you have to reflect back and remember that we are using a power grid and a system that was solely designed and implemented and put in place to power incandescent light bulbs, resistors, and we're hardly using any of those compared to everything else we're using in terms of solid state loads. So we really do need to update the system. That's number one. One of the things that the Transformer Association and the industry really does need to think about is I'm comfortable that the transformer manufacturers will survive. There's always going to be a need for that power conversion. Where we really need to focus and work is on the raw materials side of things. Steel is going to slowly be phased out for higher frequency materials, and one of the challenges we have are how do we get higher frequencies and higher performance cores better than what we currently have in the supply chain. Insulation materials were discussed. What can we do to get higher voltages, higher insulation strengths, and all of this at a reasonable cost? Because we are always going to have that. What is the cost of a 50, 60 hertz power distribution transformer versus a high voltage, high frequency system? Cost is critical, and the whole supply chain is going to be key to making this work.
Excellent. Thank you very much. So at this point, I definitely want to invite all of you to ask any question to our panelists. They're really experts in their field, and if anyone has any question of any type, this is a very nice moment to ask. If not, I would like to actually explore a little bit more about the standardization and regulation things, aspects of this, in the sense that how do you think that, this is new technology that is going to substitute a very old market, very old technology, most of it with more than 100 years of age. So there are plenty of norms and regulations and standards that any new thing will have probably to meet. So this is a question for all of you. How do you think that, the industry, a manufacturer getting into this industry is going to deal with the standards that are now in place and this regulatory framework? So anyone would like to start?
I can just make a quick comment. Is one of the issues we already start facing is the traditional transformer installation standard and testing requirement. How does that apply to a solid state version of a transformer? So because now you have electronics in it and you have semiconductor packaged, not for that kind of voltage testing situation. So we have to look at whether we should follow the traditional transformer testing procedure or we need to have a new standard which is more like a medium voltage drive side or other electronic industries following. They don't do BIO tests up to 6.9 kV. So if we have to do, you have to have a new class of technology. I just see there is a challenge to meet that kind of requirement for a semiconductor device package technology, for example. And how do you test the installation requirement of a 10 kV device up to 6.9 kV? And should we look at that? So I just say this is a potential area for discussion in the standard committee and other areas.
I'd like the guys' views on standards on terms of components, but from an application environment, we've been out there working with the IEEE Transformers Committee, a variety of other standards committees, and what Alex said is when you have a technology like this that involves so many different aspects, you can't just look at one standard. The one that we obviously looked to originally was ANSI C57. That's the transformer standard. And so we went down that path, but what we started to realize that the majority of the specs inside of that standard weren't applicable. So you have to start to tie in IEEE 2030, which is a COM standard, IEEE 1547, and some of the other smart grid standards that are out there, as well as some relay standards and a variety of others, and kind of pick out the best things that are most applicable out of the other standards, and take it to the overall IEEE committee and say, this is what we have. This is their best guess of how as move forward with the standards. But I'd like to hear your guys' thoughts on components as well.
No, I can't touch this.
So I get that the point is between kind of trying to fit in the old standards or trying to progress towards a new set of standards that will take into account the specificity of this technology, right? I think that's the point. Well, good.
With respect to drives, the IEEE 519 has been out for some time for harmonic standards, and now they just recently updated that in March of this year. So they now included some other things like near harmonics, not just the integer harmonics that you normally would see. So that can take into account then some of these other types of devices, like active front ends and other such devices, which will also be on the grid. So that's been updated recently. For the motors, there's the MG1 standard. I know they had added parts 30 and 31 talking about motors which are on either on drives or on power systems that have a lot of harmonics associated with it. And so they've got some standards on that with respect to what peak voltages the motor should be able to handle, what the DVDT should be on the voltages that the motor should be able to handle. But I think we'll see that even expanding further. I think they should start talking about partial discharge as well in terms of motor insulation systems. So we've got those two key standards. Now for UL, they've got UL 508C for low voltage drives. For medium voltage drives, they have a UL 347A which isn't a full standard yet. It's sort of, here's some recommendations, and it's a good idea to follow these things. But I think that's going to be expanding further in the near future as UL and manufacturers start producing medium voltage drives, and they become much more popular in the marketplace as well.
So another question that I would like to put on the table, and that's a very wide thing, is reliability. Reliability concerns. So for a long term, I think the industry, electronics has been seen as something that is not so reliable as a heavy mechanical stuff, something that doesn't break. So this I would expect to be a major barrier to implementation of all these technologies of power electronics in the power grid that must be very reliable. So does any one of you want to make any comments about this topic? General reliability of both the basic devices, the final devices, reliability questions. I think that's a very important point. So, for example, Jeff, do you want to?
Yeah, I can start. There's a couple of points. I think one is all the applications that silicon carbide is going into currently is usually very high reliability applications. So we're in automotive, we're in solar inverters, industrial power supplies, and these are all pretty rigorous replied. In fact, we had one tier 1 automotive supplier recently visit us, and we said, well, what is your PPM target, parts per million failure? And he said 0. We don't want anything to fail. Now, obviously, we argue with him, but that's their going in position, that nothing should fail. So I think that's something that we're used to seeing. And the other point, and this would be probably more for Chad and Alex to speak to, but we've had some customers come to us, and they call the solid state transformer. We want a solid state transformer. So we say, well, what is it you want? And what they give us back is really a definition of a power supply. It's smaller power, and it's more dividing things and taking say a higher voltage pin from the substation all the way into point of load and dividing it up into smaller and smaller units. And they save costs that way because their cabling costs go down. They eliminate some of the other expenses they have. The efficiency goes up. But if there is a failure, they only have that one single point of load failure, as opposed to if a large transformer fails, they lose everything. So they kind of view there as an upside. Again, it depends on the specific application, I think, of what you're looking at.
I'll add a little bit. That's the first argument we hear, especially in the electrical distribution grid for today's utility, is how are you going to survive 20, 30 years in a harsh environment? And the immediate reaction to that is that power electronics have been put in harsh environments for a number of years. Look at the UPS industry. UPSs have been in maritime applications, military applications, and I have personal knowledge knowing that those devices and those electronics have survived 20, 30 years in harsh environments. Saltwater, sand, humidity, et cetera, go down the list. And so very little returns from those. So point to those applications. But to solve the utilities concern, again, what we point to beyond those applications is an evolutionary of technology, right? And I started off in the introduction saying that we're not going to utilities today and say, let's rip out the transformers. What we're saying is that we can offer you a whole host of additional benefits with power electronics on the secondary side. And if there's any catastrophic event inside of the device, inside of the unit, you bypass around and ensure that your customer still gets power. It takes a lot of pressure off of the application at that stage to say, we bypass around, will act as a copper wire, and you don't get the supercharger, if you will, and you still get power to the homes. And so that gains a sigh of relief in the sense that you're not going to put a customer in fire.
Just a comment on that. Just coming from the industry and so forth, when you mentioned, that you put these in military applications and so forth, the standard for military application if you're going to run a missile system is much different than powering loads in the home. The derating factors, the temperature requirements, and so forth, so it's a bit disingenuous to say, well, we put it in military applications and it's fine. The standard that we have to meet is much, much different. And I guess the other question we have in terms of, source and saying if you have a transformer as a single point of failure, you only have one piece. But if you have a parallel system where somebody's using a DC to DC converter or whatever have you, and you have parallel loads coming off of it, if you have a single point of failure on the main system, you're going to lose capacity loads as well. I mean, you can't have it both ways. If you have a transformer failure, a solid state transformer failure, you lose both.
Right, and I don't know, I mean, some good comments. I don't know if there's a question underneath there, but here it comes.
Just to say that we put it in military applications for solid technology, that doesn't take into account a picture of what the technology is the integral portion of the solid.
Right, and I think what we see is maybe a poor correlation in the sense of utilities and people making buy decisions in this sort of equipment saying it's electronics, which I have electromechanical solution out there. So, electronics or electromechanical solution that's been out there for 100 years that is proven versus electronics. Well, I know personally at home I go through a TV every 4 years, 5 years. Am I going to have to replace an electronics-based transformer every 3 to 4 years? And all we're doing, and my major point was that is that when you look at the power electronics, companies like CREE and others have, that they go into a variety of harsh weather environments that aren't consumer product based. They're going into a variety of different applications that can withstand harsher conditions. And I don't know if you can add more to that, but
I would just say and again, it's kind of reiterating, but we do face that a lot. I think one of the most stringent we have is automotive, but also rail is another one where it's starting to emerge now. The medium voltage 3.3 kV devices and up. Mitsubishi's using it in Japan, and our devices are being run in a lot of customers' locations now on the trains. So these are 7-year design cycles. They have to survive everything from Siberia minus 50 C. I forget the high end is like 150, 160 C. And it's quite a bit of power, and they make sure they're, everything has to, I mean, you obviously can't have a high-speed train go off the track, so everything has to be extremely reliable. And so that's something we build in. I don't anticipate, kind of back our broader point, with these utility-based, I think it's going to be a slower adoption because of that, just the same way it is in rail, but I think it is going to happen.
It seems like component reliability isn't the only thing we have to worry about. I mean, there's other failures that occur. I mean, there's lightning strikes that can take equipment out. It seems like squirrels, for some reason, just love to sort of get their nose right there on the high voltage side, and they become carbon. But so it'd be nice to be able to take care of some of those other issues, or branches falling onto power lines. Maybe stuff should also be put underground, and maybe that would improve really the reliability of having power available, and really with the uptime there. So there's a bigger picture to it than just components.
That's important, and taking a look at the evolution of the grid, moving capabilities downstream to the edge and being able to route. Again, we brought out a couple different times. You're looking at the totality of the electrical distribution grid, not just a component. And so reliability is a much bigger component. And when we work with utilities, we say, hey, one of your major problems is if your branches or a critter gets in the line, you're facing all 2,000 customers downstream of that fault location to be out. How about the capability, again, to take what Jeff said, that capability of the substation to package it much smaller and to be able to put many more of those downstream of that substation? It's a very valuable proposition to utilities.
So we have another question here, so let's listen to it before. Thank you.
Hi. In more mature markets, you're going to see a period of transition. So you're going to have to retrofit, and it's going to take a while. However, what is the take of this new technology in new emerging markets? Do you see a huge adoption of this technology, or where do you see this technology at outside of more mature markets?
Good question. So the hybrid, right, for an established market is what we're seeing right now, and you're seeing that come by way of hybrid distribution transformers. E.ON in Europe is deploying, I think this year, 180 units out in the field of electromechanical, electronics-based transformer. Australia and a couple different utilities have started to move forward with hybrid solutions. But I assume that you're referencing more of the emerging areas like Africa, and where we always point back to the communications and the telecommunications leapfrog situation, where the wires and cable infrastructure wasn't put in, and many areas just jumped to the cellular infrastructure, so bypassing that completely. One of the things that we're seeing right now that adds to that market, that makes this capability or this solid-state transformer more interesting, is in those same areas you're seeing distributed generation much more prominent, because it doesn't make sense to put in a large generation facility and transmit power across extremely long distance to these remote villages and towns. So you're seeing solar penetration. You're seeing pods of solar penetration and wind, renewables, things of that nature to power these smaller cities. And we can point to North Africa as a region of electrification. That's one most specifically. So there is a strong interest in, again, leapfrogging the technology for the reasons of distributed generation, and not necessarily economically or politically feasible to put in a large generation.
One of you have any other comment on this? Okay. So thank you for your question. So while we were talking about reliability before, I will also say from my perspective that that is an absolute key point, and it's going to drive adoption of this technology all around the world. And well, at this point, I think that if anyone has any more questions, that's okay. Otherwise, I think we could wrap up and draw some conclusions from what we said today. So good? Okay, so we're going to have 1 minute or 2 minutes each to draw some conclusions. James?
What was mentioned about the rail industry being an interesting model for reliability and cost effectiveness, I think is a really good comment. My company, in terms of the magnetics that we produce, serves the industrial, rail, and high-end military. And you're never going to, we can get reliability. As Chad said, you can definitely get reliability in harsh environments, but there is a cost penalty. And you won't get reliability if you really try to cut costs out of the system. So we see the rail industry as a really good model for how it's been done. And interestingly enough, ABB, GE, Siemens, Alstom all happen to be in rail and in power generation. So it's interesting to think about that. Reliability is going to be key. Cost is going to be key. The actual raw materials that go into the transformers themselves to operate at higher frequencies, at higher voltages, are really critical to the supply chain in making all this work.
Yeah, my final remark will be, this is an exciting technology, still require more innovation. My colleague here has touched upon an issue related to reliability. So component level reliability is, to me, is not necessarily a major bottleneck, but we do need more innovation to improve the reliability of the component. And semiconductor, we're going to use potentially actually has a probably better reliability than some of the other technology, like the high voltage capacitor that might be used in this technology. And what innovation we will need to either reduce the use of those more vulnerable components or improve the reliability there. On the overall industry adoption issue, I think looking at this high-value new energy infrastructure applications such as fast charging infrastructure for the EV industry, the PV photovoltaic, and storage integration, those will be the key area to look at initially. And I think in the university, we also want to work with the industry. We need more industry involvement in this area to work with us to move this technology forward.
I see a couple of things. One is if, say for motors, if the insulation system on the motors could be drastically improved, so that the PD is a lot less and really non-existent, and also that maybe the insulation is going to be a little bit thicker than it is today, you might say, wow, that's going to be a problem. The motor might have to be a little bit larger, and that means higher cost. But I think we have to say the initial cost is not really the key driver here. We're talking about systems that are going to be running for 20 years. It's really the operating cost that's going to be the key driver. You might have to pay a little bit more for the motor up front, but you're going to get that back in terms of a higher efficiency system later on. And so that means if you don't have to put filters in, which have losses in them, if you make the motor a little bit larger, that might mean fewer losses in the motor, so the whole system becomes more efficient. That means your total running cost, the cost for the user, the end user, is going to be lower. And so we have to think more than just initial cost. We have to take a look at lifetime cost. And I think that has to be a piece of this as well. So I say insulation is a key thing, and not just be fixated on the initial cost, but take a look at a lifetime cost.
I'll just add some final remarks. Again, if we look at the evolution of this technology and the readiness of the readiness of the market's there. What we're seeing already is, again, in many different applications, the desire to connect a variety of distributed generation sources. We can pick apart any power system. I spent a lot of time talking about the electrical distribution grid, and if we look at the electrical distribution grid one more time, it's evolving to a way that there's so many renewables in the grid that many regions are at this point saying, wait, hold, we've got to catch up with our grid. No more renewables on our grid. We can look at Hawaii. There's numerous other states. There's countries in Europe that have said, we're not ready yet. And so they're waiting, looking for a specific technology that can help them manage those renewables. Efficiency, better reliability, or routing. And I mentioned reliability from a overall electrical distribution grid when it's a system, and the better. The more capabilities to again reroute power. And so utilities have, and any installer of a power delivery system have a need for some new topology and new electronics on board to be able to help them solve the problems. So the momentum's there. The train is leaving the station at this stage. Now again, will it be tomorrow? Probably not. But will it be in the near future? Yes. And have we demonstrated great progress with components, with research, and with actual live utilities doing demonstration programs? Yes. And so the reality is, you will all witness this momentum in the future of electronics or power electronics coming into these applications, thanks to a lot of the work of people on this panel and many other companies out there. We're not the only ones that are focused in this particular space.
We probably should let Chad go last. I think that sums it up. I mean, the silicon carbide, from our perspective, the first solid-state transformer that I was aware of was built about 2008, about 6 years ago, using these 10,000 volt MOSFETs from CREE. I know other people did them too. I'm not trying to just say it was CREE, but at that time I didn't understand what a solid-state transformer really even was. I kind of loosely understood. And 6 years later, to be honest, I don't still think, as an industry, we appreciate all the functionality it can bring us. At least I don't. But I'm seeing every day, this is something that could really change everything. It's something that we should be very, very excited about. Whether it's emerging markets and bringing on power in a distributed form, or whether it's just making our grid more resistant to whether it be attack or just bringing on other sources of power. It can offer a lot of functionality, and now we have the components that are getting very commercial now. So in the last 6 years, we've seen silicon carbide as an industry mature quite a bit. It's in a lot of very high reliability applications, so this is something we understand, and we know utility, anything with utility will be high reliability, but that doesn't bother us in the least, because every market we've looked at has had the same type of barrier to it. So we focus a lot on that because that's where silicon carbide technology makes sense. It's high voltage, high power, high reliability. And I think as we get into it, it'll actually, it's a very rugged technology for those of you not really aware of it. It will offer some things in the future that we probably haven't exploited yet. It's very resistant to radiation, electromagnetic pulse, things that you worry about conventional semiconductors getting destroyed in. Silicon carbide takes this type of punishment relatively easily. So it's something that will be really interesting in the next few years to see how this works out. But personally, I'm very excited to see where this solid-state transformer technology goes.
Thank you. So at this point, I think it's time. So I really thank you very much, all of you, for being here this morning in this initial panel. Thank you very much to our panelists, and I hope you enjoy the rest of the show. Thank you for being here.